Okay, recording in progress. Okay. Is that legible for everybody in the back? Yeah. 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 What was that? I can try. That work? Okay. Also, can you hear me back there? Okay. Let me know if that changes for whatever reason. All right. So my plan was we will just go through the practice exam. Again, I did post the solution on Canvas. So you have that to check against. Apparently I can't have it up while I'm doing this or whatever, just all the screens I'm using here. But that being said, yeah, I'll just work through it and kind of do it from memory. And yeah, catch me if there's any mistakes. I guess my point is, if anybody has any specific questions ahead of time, right, we can start there. And if not, we'll just start going through this.
Could you go over question 4 on the last? Would that be a possibility?
I'm going to save that for later. Maybe we'll go through it. There's one or two problems here that I would like to get through, because I think they'll be useful to get through, especially this first problem. Problem 4 in the last homework. What was that?
So in your
Okay. The solution for homework 5 is also posted. I didn't get to it till this morning and forgot to upload where it's going to automatically upload last night. But it is on there, and so you can check that out too. But yeah, we can go over that one quickly as well. All right. But we'll start with this because I think this will be probably the most useful problem and most interesting problem. All right, ready? So start with this. We have this vortex system. This is something this is a kind of a simplified version of what we're going to do in 306. And it really relates to like how the wake of an aircraft, put it that way, and then how we end up determining what's called induced drag, which is like a 3D wing effect, right? Everything we've been doing, or most of the things we've been doing, are 2D. And so this is, yeah, like I said, kind of a simplified version of what we'll do in 306, which I don't know, thought would be interesting to kind of tie that in. Oh, see if I can get all this stuff to go away. So to continue with explaining it, what the question is saying or asking is you have an aircraft, kind of like in the picture. An aircraft is flying either at or away from you. In a sense, it's not a huge, doesn't really matter which. I guess the coordinate system would say behind, but that doesn't matter. What you're left with is, in a 2D sense, you've got the two tip vortices. We basically see them here in this picture, that are kind of from the wake of the aircraft, that are kind of behind the aircraft. And what you're trying to figure out in this problem is if we have another aircraft flying adjacent, like near the wake of the original airplane, where can we fly that will get the most benefit? And what that means is, where do we get the most upwash? So like vertical component of the velocity because that is going to act as kind of a, I wouldn't say a cushion, but if you can think of, for the pilots in the room, or even if you're not, right? If you imagine you have the airplane all trimmed out in flight, and then you pull back on the throttle and you kind of let the airplane descend at a constant speed, right? But if all of a sudden there's kind of an updraft of air that matches how fast you're sinking, you will keep flying along at the same altitude, even though you've reduced the power. So that's kind of the idea here. And in a practical sense, right, you see geese and all sorts of birds, right, do this all the time, where they fly in formation, taking advantage of the upwash. So what the problem is asking is to figure out between these 3 points, it could be more precisely written in the sense of figure it out in the whole scope of the flow field or something. But given these 3 points, figure out which point is the most economic or efficient, or basically you maximize the upwash, okay? So as it's drawn, right, all 3 points are distance d from the origin, right, of the coordinate system. Just using your intuition, which one would you say is the best? Okay, somebody that hasn't talked through this.
Point B.
And why?
Just think about it, it's like a circle. At point B, the instantaneous velocity is only going up because it's together. For a circle, it's velocity is going to be perpendicular to the radius. At that point, it goes up.
Yeah, so exactly. You end up at point B, where when you consider both of these vortices, the induced velocity from the vortex, right, is entirely up, and is a contribution to the upwash. If we talk about point A, right, the induced velocity with the vortex is perpendicular to the vortex. So if we go out here, the induced velocity is like that, right? It's perpendicular to, the vortex itself. And so only a component of it is actually pointing up. So that's kind of the main reason. Intuitively, right, you'd probably say point B is the best. There is, in the way this is mapped out, there is also another reason. That's not quite as obvious.
Is it because you're going to have some contributions in the other direction, the other vortex?
That is true. The other vortex is going to definitely play into this. It kind of falls into the same reasoning. Yeah, the way it's drawn, A and C are a little bit further from the vortex itself, right? Because they're all the same distance from the origin. So these points are kind of just inherently a little bit further away because the vortex strength drops off as like a 1/r or 1/r squared. You're going to get where point B is just going to have the highest induced velocity, right? So that's the kind of thing to ask yourself, right, when you approach a problem like this, an actual engineering problem. Because this is honestly, if you're going to go, your company is trying to, design an aircraft that's going to fly in the wake of a C-130 or something, which is, C-130 is heavier than this, but roughly the idea here. And the first thing you want to do is, what's the benefit going to be? This is the kind of analysis that you could do to actually say, hey, maybe we can end up making the airplane 30% more efficient by just flying in the wake of another airplane. And then you use your intuition again to kind of help narrow down the contestants, and you start with point B. Now, the caveat is we're all engineers, right? So the objective here is to actually then do some math and quantitatively demonstrate that this point is better than the others. Okay? With me so far? Okay, so now we're going to start doing it. How do we start? Yes, that is the starting point. You're given the weight of the aircraft, right? And the strength of the vortices, these guys. And the lift can basically be approximated with the Kuta-Joukowski theorem, and assuming that the circulation is distributed or uniform across the whole wing. Written another way, the lift equals the per unit span lift times the span, which is rho b infinity gamma b. And so we can solve for gamma. which equals, and I'm going to say this is equal to weight, assuming the aircraft's in steady level flight. So gamma equals W over rho V infinity B. Now, some of these we know numbers and some of them we don't. Whoever put the problem together forgot to include a velocity. What you'll end up seeing is the relationship between the 3 points doesn't matter. It's not dependent on velocity. It's the absolute, like the magnitude that you get is dependent on the velocity because it's dependent on the circulation. But the relationship, or like which point is stronger or not, is purely just based on the system and distances and things like that. So, but if you want, you can go back later and prescribe, hey, this is flying at 200 knots and it's at 20,000 feet in the air, so the density is 0.0018 or something like that. But as far as, again, forgetting not having a V infinity or a density even prescribed, we're just kind of work through it with symbols. Okay, so we do know gamma. That's a good one. What's the next step? The weight. That's true. Yep. We're going to want an equation to find the vertical velocity. How do we start into that? Yeah, we can do that. How do we get to there? Huh? Equation sheet? That would help. We do have to model potential flow. There we go. Yes, so we have to set up the stream function with the two vortices, or velocity potential, whichever you're more comfortable with, prefer, whatever. So we have two vortices, right? I'm going to call this one 1 and this one 2. So our stream function, total stream function equals stream function of 1 plus the stream function of 2, which is going to equal don't look at me. I already know how to do it. This is for you. Yeah, we're not getting the problem 4 at this rate. Go ahead. Okay, so stream function equals negative gamma over 2 pi ln of r.
Wait. Gamma over 2 pi. Over 2 pi times ln of r.
Okay. Yeah, I don't have my notes because I'm using my laptop to get the, I guess I could pull it up over here if I absolutely need to. But I'm hoping if I make a mistake, somebody can just walk me through it. Okay. Now I have my solution up in case I need it. So, yeah, it's kind of warm in here. I don't know. You can crack the door if you want. I don't know if that's going to help at all, but all right. So we have the stream function, right? for the vortices over here, right? That's for a single vortex, right? Also, where is that single vortex? In the problem they are. Well, in the problem is two vortices that were where the wingtip was, but or are where the wingtip was, but that's okay.
Both are located B/2 from the origin.
For the problem, yes. This definition though of the stream function, where's the origin there?
That's like modify it the origin.
Okay, yeah, that was the next question. Yeah, you have to basically take this relation and shift it so that you have two vortices that are at the wingtips, right? Because this R is assuming you're at the origin. So this is where it's kind of easier to jump to Cartesian coordinates to do this. We do this with, right, R equals the square root of, I think I put it in the notes or the, yeah, in the slides or whatever, where it's x minus a squared plus y minus b squared. Right, and so that's going to shift the radius, or the center of kind of where we're taking the radius about, to wherever we need it to be. Fortunately, we're not shifting it up or down y. We're assuming everything's just kind of in one plane, but we have to shift it over to the side. So this a, right, is going to be either b/2 or negative b/2.
Can we take the radius from the origin? Like if we know that D is 75 feet.
Because the strength of the vortex, right, it's like the strength of the vortex is a 1/r relationship, but for the velocity at least, from where the origin of the vortex is.
Okay, so it needs to be at the center of the vortex, not necessarily the center of the system.
Yeah, yeah. I think there are ways you could basically shift it in polar. It's just kind of easier to shift it in Cartesian. It's also going to be beneficial because the problem itself is asking for the vertical velocity, right? The reason it's asking for the vertical velocity is because that's what's going to help the airplane that's flying in the wake here or flying outboard at the tip in the upwash get affected by, resisting gravity. If it was just what's the absolute velocity there, then it might be pushing that little airplane somewhere else.
Could we technically put two of those equations, except have one be ln on one and one be ln on two, and then just find the distance from each vortex and then add those velocities together?
I think you're getting at what we're going to do. I think what you could do though, as a totally different way of approaching this, and it would be just as valid, is you could shift the origin to the center of this vortex. And then you only have to shift one of these relations in Cartesian. That's another way you go about it. Get the same answer. Might be mathematically it's a little easier. But again, that's just not what I have worked out in the solution. So, okay. So with that, we have this relation for R, right? We know A is going to be plus or minus b/2, right? Okay, just making sure everybody's on board. Anyway, looking at an individual. So I'm going to rewrite this out, right, using these relations. I will say, if you saw the note that I mentioned in class, or sorry, I mentioned the announcement for the class. Basically, we are defining positive gamma as counterclockwise, right? Which is complacent with the right-hand rule. Like we had talked about this in office hours, and I think I even pivoted, but basically the notes, all the notes we've worked through are where the positive circulation is a counterclockwise vortex. You'll see in the book where they do it opposite. The reason for that is because that way you have positive circulation produces lift. We'll kind of, again, in 306, we'll be kind of revisiting this stuff and we'll probably do it in that notation. But typically in airfoil, we draw the circulation like this because this is the circulation that would give it positive lift. But again, if you kind of work out the right-hand rule, this is opposite of the right-hand rule. So anyway, just for the course and for clarity, we're going to work it out for as if the right-hand rule is what's going to give us positive circulation. And that's just going to affect the negative signs you'll see here in a second. So first we're gonna do this vortex, right? So its location is at negative b over 2, right? So when we substitute everything in, it's going opposite, but we have opposite of a negative, so it ends up being a positive 2 pi. And then ln, and it's going to be the square root x. It's negative, so it's plus b over 2 squared plus y squared. And then for this vortex, again, I kind of scribbled all over the negative and stuff. Basically, this one should actually, I'll just cross them out here. That one should be negative. That one should be positive with the notation that we've been kind of using the notes, right, where it's counterclockwise positive. At the end of the day, when you work it out, you'll end up getting where the answers are negative or positive, and it kind of makes it obvious. But anyway, just to keep it consistent with the class as far as we've done. So this one's negative, that one's positive. So we then have, we're adding them together. So then we have negative gamma over 2 pi, natural log, square root, x minus b over 2 squared plus y squared, and then close parenthesis. Okay. Everybody with me so far? So, yeah, good question. This is number 1. And this is number 2. Right? It's at negative b over 2. That's why we have the positive. And then it's acting in the clockwise direction, which means it's has a negative out in front. But for our relation for the trying to like, maybe I'll switch colors to pizzazz. Over there, right? It's defined with the negative in front, so it flips it to positive. It gets your attention. It pops. Okay, so that one becomes positive when we account for the negative out in front. This one was positive. We have the negative out in front, so we keep the negative out in front, so now it just all becomes negative. And then the shifting that happens is just from the equation of its negative, and we're at positive b over 2. Okay. Okay, so now we have the stream function. What do we do now? Somebody said it over here earlier.
Find the vertical velocity by taking the derivative with respect to y.
So you have the vertical velocity. Is it with respect to y or x?
Stream. We're doing stream.
We're doing stream function. It's negative partial stream function partial x. That one is just, yeah, from the equation sheet. Does everybody feel like they know where to go from here?
It'd be easier for us to take the derivative in polar coordinates and then convert it afterwards.
Well, the one trick you can do is for this term, say we're looking at term 2, you can say this negative gamma over 4 pi ln of x squared minus b over 2 plus y squared. So since it's natural log, we can take the exponent out. And that makes it a little bit easier. Huh?
The X squared the X.
Oh. I don't know why I keep doing that. So that makes that a little bit easier. You could convert this back to polar and then take derivatives, but it's kind of a preference thing. Again, you should end up with the same answer. You will end up with the same answer. It's just kind of what seems mathematically the most straightforward. When you do this, when you take the square root out, it makes it pretty straightforward to work with. So just to finish this out, right, what we're going to have is gamma over 4 pi, doing the same thing to the other ln, the other natural log here, times, but everybody know what the derivative of the natural log is? Yep, 1 over x plus b over 2 squared plus y squared times 2x minus gamma over 4 pi times 1 over x squared minus b over 2. I did it again. Plus y squared times 2x now what do we do? Stop and take a coffee break? That'd be nice. We just plug in the values, right? So use trig to figure out, obviously b is pretty easy, right? It's x equals 75, y equals 0. For the other points, you can use trig to figure them out, or you could convert it to polar coordinates and then plug in r and theta, you know, whatever floats your boat. I'm just going to do point B here because it's, you know, easy to demonstrate. So what we're going to say is b at 75, 0 equals gamma over 4 pi times 1 over 75 plus, what is this? 100 over 2 squared plus 0 squared. I guess I'll move the times 2 to the numerator. Minus gamma over 4 pi times 75 minus 102 squared plus 0 squared. We can also plug in what we have for gamma. So this one's going to end up making sure this works out right. It's going to be 25 squared. This is going to be 125 squared. Let me see. Oh, forgot the negative out in front here. So that distributes there. That becomes positive. That becomes positive. This is negative. That's a pretty big deal because that's where, again, you get where like all the velocities are flipped. Again, that's where starting the problem with like, what do I think should happen is kind of a good starting point. Again, things get pretty complex pretty quickly. This is a relatively simple flow field in a sense. But to kind of step back and ask yourself in a gut reaction sense, does this work out? Because I was just looking at this and saying, hey, this denominator is much bigger and that one's much smaller. Or basically, this side of the relation is going to end up being smaller than the other one. And if the other one was negative, that would mean the velocity is down. And we know that's not what's happening because you've got this vortex that's throwing air up, right? So it was kind of a gut check of where did I drop a sign somewhere in here and go back and find it and fix it. Okay, so just to kind of collapse it together and write it a little nicer, what we have is gamma times 150 over 4 pi multiplied by 1 over 25 squared minus 1 over 125 squared. This is where we can go back to that gamma definition we came up with earlier and plug that in. So it equals W over rho VB. Actually, here's what I'm gonna do. I'll make it 150, why not? Something like that.
So when you were taking the derivatives onto top and you multiplied by 2x for both of them, why is it just 2x, not 2x plus maybe and 2x minus 2?
It probably should be. X squared plus, what is this going to be? X bx, yeah. Bx plus b squared over 4. Yeah. That's a good question. So the question was, would you get the same answer, or can you do this with the velocity potential? Anybody know? Yeah, you get the same answer. One might be mathematically, again, more straightforward. It kind of depends on doing it. You know, once you've done enough of these, it's kind of obvious one's easier than the other. On the other hand, I find where the string function, it's easier to like forget a negative, or again, the derivatives are always the opposite. So it's like instead of for the x velocity, right? Instead of being partial x, it's negative partial y, and it's just kind of easy to like forget things. So sometimes the velocity potential is easier to use just purely from that perspective.
The velocity potential we had it theta instead of ln of r here. How would we go about older?
So the question is, I'll get to your thing in a second. In the velocity potential, we have a theta instead of an r, an ln of r. And if you go to the like extra trig stuff slide, yeah, you have to use arctan to get to theta. And then if you take the derivative of arctan, it's like whatever the quantity is squared divided by, or the derivative of it divided by 1 plus that thing squared. So again, the calculus gets more elaborate, but yeah, that's how you go with that one. Yeah, what's up?
Give us a question we want us to velocity potential. Would you give us one where we have to the derivative of like an arc tangent? Or like a
Potentially. See, that's a pun, you know, velocity of pressure. It's possible. On the homework, I think there was one, right? So it's hopefully fresh in your mind. But no, I'm not going to have you do like giant elaborate intervals for, you know, hyperbolic tangent or something. Which one? Probably for the second numerator. Oh. I don't know. I'm just going to get rid of this simplification row. That final relation, you can plug stuff in. Where's the B coming from? Yeah. It's coming from the chain rule. So up here, right, we took the derivative of ln of, where is it? ln of x minus b to the 1/2 squared, or b over 2 squared and all that stuff. So when you do the chain rule, right, then you're going to multiply the whole quantity by the derivative. And they kind of pointed out, I missed it the first time I did it too, that when you expand out this denominator, I don't know where you went, but there you are. When you expand out the denominator, you get this, right? And so it's not just 2x, it's 2x plus b. Because there's an x there.
Go over question 3.
Sure.
Thanks.
Is everybody kind of comfortable with this?
The other one should be minus B.
Yes. I fixed it down below. I did not fix it here. Yeah, that's a minus b. Okay.
Basically, just evaluating B at points A, B, and C. And this is the debt.
I just did b, yeah, because it was easy to. I'm kind of waiting. There might be a question over there, but otherwise, yeah, we can jump to problem 3 if that's fine with everybody. Everybody okay? So again, to pair, go ahead. Yeah. The angle comes into play, right? That I need to figure out V at 75 times cosine of theta, and then 75 times sine of theta, right? And then negative. Because we're working about the origin. Make sense? Okay. Everybody comfortable with this? Feel a little better about it? Okay. So to paraphrase, again, if you've got like a potential flow problem like this, right? Start with either the velocity potential or the stream function, right? To basically, the word to use, define your velocity field, right? Or define your field, not necessarily velocity field. You'll figure out the velocity field in a second, but define your flow field. So in this case, we had 2 vortices, right? So we added both of those vortices in. We had to account for them being shifted, right? So that's the step here, right? Is we basically defined that the stream function was the total stream function for the whole flow field is going to be these 2 stream functions added together. We defined them both with the shift, right? And then we just kind of worked through the math, or simplified a little bit, and then worked through the math to figure out the velocity, right? We did that by taking the derivative, which again, if you go look at the notes, it's a pretty defined thing to do. And then with the once we had the velocity, again, being the derivative of the stream function, we could just plug things in to figure it out. What if this asked you for the pressure at these points instead of the velocity?
One minus V over V.
You could, yeah, you could, well. You could, there's a more straightforward way. If it asks you for the pressure coefficient there, that's what you would do.
Just use the number.
Yeah, so you'd want to use Bernoulli's. You'd want to say, and it gets a little bit squirrely because there's this other free stream velocity that's kind of not in the picture. And so I would basically say we're just working in 2D here, right? We're only kind of working in this plane. What is the total pressure? And so you're just working with the velocities, but yeah, you basically use Bernoulli to relate, again, what's a free stream pressure to the pressure at those points because you have the velocity, right? Bernoulli's is useful for relating the velocity, the pressure, static pressure, and the dynamic pressure.
That would be like an additional step to what we don't do.
Yeah. Yeah. Yeah, it'd be an additional step. Yeah, where you exactly. You basically, the whole process up to this point would basically look the same. The caveat is when you have to assess points A and B, you have to use the total velocity, right? Or sorry, points A and C. At B, it's easy because the total velocity is just the vertical component. But at A and at C, you have this other component of the velocity, right? And for Bernoulli, we need the magnitude of the velocity. Okay?
So in that case, we just have to find, instead of without V, we'd also have to find U and then for the X.
Yes, you'd have to find V and U, then take the magnitude of those vector components. Okay. Everybody on roughly the same page?
Question about the pictures though.
Mhm.
When you're doing Bernoulli, is the plus P pressure term we're adding over to the static pressure? Really initially, so that would be just like atmospheric in this case, or
You'd be given some kind of atmospheric pressure that's, again, this one's kind of goofy because in theory you're like moving behind an airplane or something, you know. But yeah, you'd be, or you could say everything came to rest, like the airplane's gone. So yeah, you'd be given just here's ambient pressure, and that's probably the total pressure, and then you've got the moving part. But yeah, you'd be given enough information to work it out.
yeah,
But yes, it would just be the ambient pressure equals, say, the pressure at point B plus, yeah, equals P infinity, because there is no free stream pressure in this case. Because there's no free stream pressure, new free stream velocity. This dovetails more into like a 306 lecture that I really don't feel like giving, but we're just going to say we're really, really far behind the airplane and these vortices just still exist. So the air is not moving, the air has come to rest, except these two vortices that still exist. Everything else has just settled itself out. So there's no free stream like you're moving into the page or anything. So this is 0, and all you have is the vortices are spinning. And so that's all you're relating. If you want to find the pressure, go ahead.
So the infinity, that's just free stream. Like it's like is it the velocity of like everything that will infinite the flow structure we're analyzing?
Yes, the velocity that's uninfluenced by the thing you're looking at.
So the only way that has like a value is if it's just a uniform flow.
Yeah. When it comes to these potential flow problems, yeah. Right? Okay. Okay, that's enough of beating our heads against that one. Okay. So another potential flow problem. And this, maybe this will scratch the itch for trying to do homework, problem 4 of the last homework. So we have a circular cylinder is spinning in a free stream that is moving at 50 feet per second. The cylinder has a radius of 1.5 feet, and the stagnation points are 20 degrees below the horizontal. Determine the strength of gamma to confirm this, or the strength of gamma and confirm this result by integrating velocity around the surface of the cylinder. All right, let's get started. Somebody say. All right. So how do we start this problem? Yeah, so we're gonna start with velocity potential or string function. Anybody have a preference?
Let's use.
Stream function, velocity potential. Okay. Okay. So let's see what I did in the solution here and how much I have to ad hoc this. All right. So we're going to start with what's the definition of a stagnation point? Did I call you? Who said that?
Sorry.
All right. So where the velocity equals 0, what components of the velocity? Huh? Okay. Well, no, I was going to ask him. Okay. What components of the velocity? Yeah. So if it's u and v, they equal 0. And if you're in polar, right, both of those components would also equal 0. Okay. So with that said, that's our stagnation points. All right, for our velocity potential, what's the first element here we're going to consider? No, there's somebody else. Later, don't worry, later. You get a harder question. What's like the first element we're going to consider here? Okay, and what's the velocity, the function for the velocity potential of a uniform flow? Yep. Okay, so that's the uniform flow. What's next? Okay, so what's the function for that? Yeah. Oh, that one. Yeah. I'll write it down and then I'll make my announcement here. I think that thing I put that PowerPoint I posted is finally free of bugs after finding like 2 more. So it's gamma over 2 pi times theta. What I'll say is for any of the bugs that are like typos or things I found in the last couple of days, if you need those on the exam, they're on the exam itself. So if there's any typos in the PowerPoint that I haven't, like basically ones that I've caught either from somebody emailing me or working through problems or whatever, like I've uploaded new drafts of it and sometimes I post an announcement. Again, as it's there, it should be, typo free. But if those typos have been caught, like basically everything I've caught up to this point that hasn't been like talked about for a week or isn't new for a week, I've added it as like a hint on the exam so you have the relation you need in the correct form. Okay. So this, for example, if you needed a vortex and you want to use potential flow, it'll say hint phi, for a vortex equals gamma over 2 pi times theta, not divided by theta. Make sense?
Yeah.
Okay. Okay, but this is our potential vortex.
Direction of the circulation, like make it positive or negative,
Yes.
since said earlier.
Yep. That one is negative. Okay.
U times R or use
Which one? Oh, for the uniform flow, it's U times R multiplied by R.
It's like big R. It's the same as big R.
It's a capital U.
No, the R. I mean, that's the.
It's a yes. The radius as a variable. because it's coming from in Cartesian coordinates where it's just equals ux. So it's that's where it comes from.
Verify little r is like a variable as you go in or out radially, and big
Yeah.
R is just the radius of the.
Yeah. Yeah, so little r, I guess I can even write a better definition of it. Kind of reusing variables here. So let's see, what should we make this? Does anybody have a favorite Greek letter that we're not currently using? What'd you say? Cap omega? All right. Usually we use capital omega for something that's spinning, but whatever, that's fine. Well, I guess it is spinning, but anyway. So that way I can say this is theta. The reason being just for defining the coordinate system, right? Again, we're working in my voice. We're working in polar, and so it's all about being a distance from the origin, and then your azimuthal position to that position, right? Your r distance, and then you have theta is kind of what gives you your directionality. Yeah.
If we were to do what you just did, like all cap omega, we like just use it as arbitrary, would that be fine?
Yeah. The reason I'm doing that is just because we're typically, right, when we're going through this math, we're using theta, right, as our other variable. This makes it look like theta is a constant. In reality, theta, it's like if I went through a problem using x and y, and then I said, hey, by the way, something is y equals 20. But then you start working through the math and you're like, well, y equals 20. So I'm going to start taking derivatives and stuff like that. And oh, y is a constant, so I don't have to worry about it. In reality, y is still a variable, but it's kind of, I should not have reused variables like that. I'll put it that way. So yeah, we'll just call this omega. Possible I may have done this in the exam too, but just you'll figure it out. Don't worry. That I might take the chance and try to address. Anyway, we'll can continue with that. Okay, so for this problem, what is the last component or last elementary thing we need here? Not yet. Hold on. So in the picture, right, we have uniform flow. We have a gamma that's spinning. What's the last thing? Yes, we have a doublet. And our relation for the doublet is kappa over 2 pi r multiplied by cosine theta. The cylinder. Yeah. General rule of thumb, cylinder equal doublet. Yeah. It's modeled as inside the cylinder, but in a practical sense, it's the cylinder is spinning.
So I don't know, so this is just-
What's that?
Doesn't the cylinder need to be like separate? Then we have like.
Doesn't it need what?
It needs to be doublet plus uniform flow, then make a model.
Yeah.
And then if one of them.
Yeah. Yeah. What's up? I can't hear you. What's up? Cylinder. So cylinder equals doublet, and I guess a good way to clarify is doublet plus free stream. Because if you just have a doublet, right, it just kind of expands to infinity. Right? If you have a doublet and a free stream, then it gets restricted to basically a relationship between the strength of the doublet and the free stream. And we're going to use that in a second to define kappa.
There was no gamma, then there would be no.
If there's no gamma, then there's no vortex. It's not a spinning cylinder, it's just a cylinder.
But the cylinder still equal double.
But the cylinder still equal doublet. Yeah.
Even if there's no gamma.
Even if there's no gamma. It's just not a spinning cylinder.
Why is it even generating?
Because it's spinning. Yeah, it's generating lift.
Okay.
It turning is turning the flow field. Yes.
Spinning. It's not spinning, but it's only close to double.
Yes.
It's simple.
Yes. Because it's spinning, there's a vortex that we're using to model it spinning. If it was not spinning, there would be a vortex. And yeah, if you have just a doublet without a free stream, it basically can expand to whatever size, right? It just influences everywhere. Because of the free stream, right, it basically contains it to be a cylinder. And we have a defined, circle. Yeah.
Does not exist without the instruments.
It exists. It's just not like a defined shape or a.
Like we won't get that one.
Yeah, like imagine just for the sake of clarity here. I have a source, right, by itself. And it's going to just go out to infinity, right? But as soon as I add a free stream, it ends up having this contained shape, right? And I could prescribe the streamline that defines the shape as a function of the velocity that's coming in, u, and the strength of the source. And that's all the doublet is in the same way. Okay? Which we've done, we actually did in class. And what we got was kappa equals 2 pi u r squared, where r is the radius of the cylinder that you're interested in. U is the velocity coming in, right, is the uniform flow. And then we have just 2 pi in there to basically cancel out 2 pi and make it easy. Good? Give me a second. Okay. All right, so we have our, oops, not doublet. Okay, so we have our flow field, right? Now what do we do? We're trying to find the circulation that will put the stagnation points at 20 degrees below the horizontal.
You can find V theta on the cylinder.
Yeah. Yeah, so we need to find V theta on the cylinder. What about VR? Let's try somebody back there. I'm assuming that the further back you sit, the less prepared you feel. So like where's somebody in the back that maybe feels like they're getting it? What about VR? What do we do for VR? Yeah? Yeah, radius is not changing, right? So the velocity for the radius isn't changing, right? You're not getting further away or closer. So that component's 0. So all we have to be concerned with, get rid of this for clarity's sake there, is V theta, or yeah, U theta, V theta. Again, U, V, kind of interchangeable. As long as you're careful and clear about it, doesn't really matter. Right, the lowercase ones are the X component and Y component of velocity. When it's uppercase, It's just, you know, kind of in the context. It's usually just whatever the free stream is.
Yeah, it's not only the case because we're finding the points on the surface of the cylinder.
Yeah, because we're just because we're finding the points in the cylinder. Yeah, if we're trying to find like the velocity over here, then we have to be concerned with v theta. If we're trying to find it like out here in space. Okay. Help? Okay. Or sorry, yeah, UR. You need UR and U theta. I said U theta, but you need both to find it out there. Okay. So U theta is 1 over R partial phi partial theta. Again, this is why I changed that other variable to something different. Equals, we start taking these derivatives. For the uniform inflow, right, or uniform flow, it's just going to turn into negative U sine theta, right? Honestly, sometimes I'm asking right because I'm like doing this here and just making sure I'm right. Next one, we have that first term, or the potential vortex, right? And that's going to be negative gamma over 2 pi. And then for the next term, it's going to end up being negative. I'm going to sub in a kappa here, just for clarity. Oh, you're right. Yeah, again, it's pretty easy to like miss little things here. That's especially when there's a negative or a 1 over R out in front. So yeah, when we get to this, the cosine becomes negative sine. So you have negative U R squared over R squared sine theta. This is also a good spot to ask yourself, like, do the units check out? That's another way to double check if you forgot something like a 1 over R. Because, for example, here on the end, right, the denominator is R squared to cancel out with the capital R squared in the numerator. The capital R squared is the radius of the cylinder, right? The doublet that we're using to kind of model a cylinder. And what I do with this, again, because we're looking for stagnation points. Yep, we'll set it equal to 0. Okay. What's the other thing we can do? Well, we'll do next, I guess. What's the next thing we do? Is that what you're going to say? Yeah. Okay. So now we plug in. We got to be a little bit careful here because it's 20 degrees below the horizontal, right? Which is like, I think it's negative pi over 9, something like that. Yeah, you're going to want to use radians. Yeah. Or whatever. The thing is, right, it all comes back to how the problem defines the things in the problem itself. Right? Our unit circle is working from the x-axis around, and the way it's defined here, it's just 20 degrees below the horizontal. So you just got to be mindful of that. What's up? Get stagnation point. Looking for that stagnation point. Stagnation points. Because that's what the problem is asking for. You don't have to. I just won't give you any points. You can find whatever you want. If you find Waldo on your paper, I'll be impressed. You won't get any points for it, but all right. So now we plug in. You never know. Could show up in the final. Oops. I'll plug in my laptop real quick.
I think the two ones. I don't.
So if we plug in negative 20 degrees, because we're going below the horizontal, what we're going to have is 0 equals negative u sine negative 20 minus gamma over 2 pi. What's the other thing we can plug in? R equals R. R squared for R squared. Also, as given in the problem, right, this is 50 feet per second. Because you guys love numbers, right? Everybody tells me you guys love numbers. You want numbers, not symbols. So that's 50. That's 1.5. That's 50. Somebody calculate that for me. I'm gonna blank this really quick. Okay. Do you have a number? Let me see. Oh, 322. Anybody else get that? Yeah, okay, cool. Because the problem is I did the solution with the over theta thing screwed up. And so the solution's messed up. I'll fix that after class or after we are done here. Give me like 5 minutes real quick for a break. Does anybody know if there's anybody in here after us? All right, well. I'm gonna try to adjust something really quick. Thank you. Yeah. Oh, we'll keep going. Don't worry.
Like this is if you don't put in negative, you get a negative measure. So if you negative, you get like that doesn't make sense because it is. Oh, yeah. The worst thing we got tricks. Something like would just have a car driver.
Okay. All right, ready.
All I'm getting right now. So is there? How late was the chicken?
Okay, ready to get back to it. Now what? Yeah. Huh? We basically defined it with a negative here in the front. So it's spinning that way. Like Yeah, really, we should get rid of this. We should get rid of that. I guess to define it opposite of the picture. Because the picture is defining clockwise positive. And so we have a negative here to reverse it so that it's counterclockwise positive. And so when we get our final answer of positive, it's now, I think, agrees with the picture. Which is, it's going to be spinning. Yeah, what we could do. What do you want to do? What you want to make spinning clockwise positive or counterclockwise positive? Okay, then that'll be going this way. Okay, and then it's that way. It's a positive there. It's going to be positive there. It's going to be positive there, and it's going to come out negative. Right, because the sign terms are both going to be negative, and we're going to have to add them to the other side. So now it's opposite, right? Our definition is counterclockwise, but it's spinning clockwise. So it's all. I can't. If you assume it's counterclockwise, that's consistent with the signs that are in the equations, and then everything should work out. Yeah. You guys, there's a lot of room up front now if you want to come down. No? I'm not staying here all night, but I'm fine to be here for another bit if you guys are. All right, so what do we want to do now? Do we want to do the other part of this problem? Do we want to move to a totally different problem? What's up? Which number 4? This number 4? Is that what you want?
No, I'm trying to clarify the sign convention. It's in the slides and it says clockwise means positive.
Jeez. I'll keep going past it.
And then just say it's.
I'll put it this way, and I'll like put out a thing that's like very clarifying after the exam. For the exam, and this is one of the things I even kind of made a note for it in being there. Counterclockwise is positive. And then the equations that are in that summary of potential flow relations is consistent with that. So if you're assuming counterclockwise is positive and you use those equations, you're good. Yeah, that I guess doesn't have to have a negative in front of it. Yeah. Some of those won't be as big of an issue for the but yeah, I'll clarify this like Friday or something maybe, and then again like post on this. Trust me, it won't affect your calculations. For example, if it asks for the magnitude of the circulation, it doesn't matter. right? I grabbed all the relations out of a different textbook because they're just all nicely in a table, easy to work with. That book uses the right-hand rule, which is counterclockwise is positive. Our textbook uses, it does, I don't know, because the other textbook also had the velocities and the derivatives and everything in like one nice area. The Anderson's book does as well. It was just, I've been using that book for a lot of other aspects. I mean, it's this one right here. But yeah, it uses the opposite because it's conventional with the right-hand rule as opposed to the where it's trying to be conventional with lift being positive.
So which way?
Counterclockwise is positive. The equations that are in the summary of potential flow are consistent with that. And any problems on the exam or whatever are asking either for the magnitude or for something else. So it's like, it ends up not mattering. Okay. Moderately happy? Not quite? No? Okay. Okay. Somebody asked about number 4. We didn't actually finish problem 3 here. Yeah. So in doing problem 3, the problem basically asks you to find integrate the velocity around the surface to basically confirm this, right? And so we have our velocity. We have our same stagnation points. We have u theta, right? So this all stays the same, all the stuff here. So we have from 0 to 2 pi, right? So we're going all the way around the cylinder. I'm going to do the line integral one here. For v, it's this, where to put it? Yeah, this relation here. So we're going to have negative u sine theta plus gamma over 2 pi r yep minus u r squared over r squared sine theta dotted with our tangent vector, which is going to be e theta hat, and then b theta. So we're basically just going around the cylinder, r is constant. Unit vector is all the way around. So we start integrating. We'll see where this goes. Because for the solution, I worked this one out. So we'll see how this comes out. What we're going to get is the negative u sine theta becomes negative well, the sine theta becomes negative cosine theta, right?
Won't it be in e theta r?
Already theta. U, yes. Let me erase that, get it closer. Yes. Yeah. Because we're only concerned with that component, right? The way it works out for this problem, you're kind of limited. Give me 1 second and I'll get to you. R, and then this is d theta is our kind of like little segment of the cylinder.
So why did you flip the signs for the gamma over?
For here?
So you also put like, before you had it written in negative.
Yeah. Yeah, so for this up here, it comes back to the problem had the cylinder spinning the other way. So I was talking with him in the front, and to kind of keep with consistent of counterclockwise is what works with the equations in the notes, in the summary notes, kind of the most recent thing that I would say, again, if you're making an equation sheet, it's what to use. Counterclockwise positive. And so I'm just redefining that it's spinning this way. And it doesn't matter, you're just going to get a different sign at the end. But being consistent with that, rather than like putting a negative at the front to kind of flip it, I was like, we're just going to basically define it going the other way and let everything shake out. And that's why we end up getting a negative number here at the end of negative 322. Because it's spinning opposite of how we're defining it spinning.
So then how come in the previous problem that we did, we made clockwise positive?
Previous problem we did, we made clockwise positive. We redid it where it's negative here and positive over here. I don't want to leave random marks. Yeah, so we have where the first term, which is for this vortex in front, the term is positive, but that's because the stream function has a negative in front of it. Over here. Right-hand rule. Yeah. And the equations with that. And like I said, it won't, for the exam, at least the second exam, it won't matter. If there's questions and stuff, they're related just to the magnitude of circulation, not like an absolute value. Or it is an absolute value. It's not asking for the actual value. And then there's things where it can play out in the math, but again, there's blurbs on there about counterclockwise being positive and such. Where'd it go? Okay, so we're back down here. Hitting around, we have RD theta. To the point, R is also important, right, in terms of units, because this is going to be length squared per second for circulation, and we have just velocity, so we need this other R to get that all to work out as well. So now if we start integrating, what we're going to get, right, is the integral of sine, negative cosine. So we're going to have u cosine theta. This one is just going to be adding a theta in here. I'll add the R at the very end. It's going to be gamma theta over 2 pi r minus, then we have the same thing, right, where it should be plus ur squared over r squared cosine theta. That is all times r. And that's from 0 to 2 pi. So let's see. This is going to give us the circulation. Let me think through this for a second. How do we apply that we need it at the stagnation points, right? Here and here, which is 20 degrees below the horizontal. Let's see. Here to apply. Here we evaluate that. We have this relation. So, let's see. Well, let's do the math real quick. I'm gonna run out of room here. See if we can add it back in. I'm just going to move down below this other problem, and then we can kind of use the space later as we need it. So they're going to end up with the total circulation, right, equals, I think this is going to end up just shaking out the equal circulation. You are data, not going to plug in data yet, plus over 2 pi r plus 2 r squared r squared cosine theta. That goes away. We can do 2 pi to 0, which is going to just end up giving us also r equals r, which we're going to just end up getting here for r. Okay, drop the r. Yeah. Well, needless to say, this won't be on the exam specifically.
Not the R under the gamma theta.
Seeing right here. Yes, that should get eliminated from the r that we're multiplying by. So that's where we just get gamma back from gamma. Well, so we just did a proof. Yeah, this was supposed to be more of a brain teaser type problem. So that's where I'll work this out later. I can tell you this type of problem won't be exactly on the exam, so you don't have to worry about it too much. In a sense, we did just prove the circulation, right? We didn't prove the numbers specifically, but we got back to what the circulation is by integrating around.
Like these type of problems, but I mean, like.
Yeah.
The city circulation problems, like from the exam point of view, should we be learning about anything except for like a cylinder? Otherwise, then our VR won't be 0, and then our DS and be to the RT then. So should we be learning about anything?
You'll be okay.
Our cylinder.
The discussion we're having as far as the spinning only affects if it's spinning. Okay?
So we don't have to worry about like the square.
No. Yeah, the things that we're doing at the moment, right? You can build somewhat complex flow fields, but all we're doing at the moment is pretty simple flow fields, right? And then as far as, like I said, for the circulation aspect, the problem has a little star, right? It's like counterclockwise is positive. If it's, if you need to use circulation in a sense. Other problems, it's more about the magnitude. And so it doesn't matter if it's positive or negative. And then for things like this, again, as long as you're using what's in the summary notes and assuming counterclockwise positive, the sign will shape out to what it needs to be, what works out. Sorry, what's up? Yeah, that was, we just kind of pick a spot. Right, since r equals r, basically the tangent vector is tangent to the cylinder, and it's the unit vector for the angular component. In this specific case, right, it's just following the surface of the cylinder all the way around. So basically this ends up just being a proof. But yeah, like I said, that one, don't worry about that type of problem too much. So does anybody want to do this last one here? Do you feel like yeah? Okay. All right, so the problem is we have the string function. I'll even write it as it's there. So our theta equals negative u a squared over r multiplied by sine theta. Okay. Does anybody know what this is? What this string function is?
It's negative u times a squared over r times sine theta.
Yeah. But do you know what like fundamental element it is?
Element.
Yeah, of our kind of elementary flows. Yeah. What was that? Not quite. It's basically a doublet. It's a doublet by itself. Substituted in with, rather than having that kappa in it, like substituting in as if there's a uniform flow. Now we don't have a uniform flow. We basically have a doublet where we kind of have the other kind of substitution in here. But again, the problem isn't necessarily asking about doublet. It's just giving you a kind of what's supposed to be an arbitrary stream function. I'm just saying it's, if you look at it, it's not necessarily arbitrary. Okay, so if we wanted to find the streamlines, what would we do? Yeah, we'd say, hey, we want psi equals 1. For that's going to be a streamline. So then it equals u a squared over r. Oop, not r squared, just r. Not there yet. Sine theta. And then maybe we multiply by r. So r equals negative u a squared sine theta. And then we, go from 0 to 2 pi, right? And we plot what the streamline's doing, or 0 to pi, or whatever kind of length you care about, and you solve for r, and then we could plot a streamline. If we want to do another streamline, right? We say maybe we're going to use 2, and we do the same thing. We have negative u a squared over r sine theta. And so now this other streamline is 2r equals, well, I guess we'll just make it easy or consistent. It's negative 1/2 u a squared sine theta, and so on and so forth. So if you want to plot streamlines, you just set the string function equal to a number, and then take one of the variables and kind of make it a parameter and sweep it, and then the other one's a function of that. But the fundamental thing to know is that you just plug in a number and then hold that number constant. Okay. Okay, so part B, determine UR and U theta. Yeah. Why not? No, we're not going to do that. Unless you want to. But okay. So part B, do we need to do part B? I see a no. How about in the back? You guys feel confident with part B? So since we're just finding the velocity components, we just take the derivatives that we need to, right? And that's the velocity components. So that's pretty straightforward. Part C, find the stagnation points. Do we need to do part C? No, you just said equal to 0. This one particularly, again, if you think of a doublet, you don't have any stagnation points. And so the functions just look wonky, and that's kind of the trick of the problem, is there's not any stagnation points. You end up getting like r equals 1 over r equals cosine theta or something. Or yeah, it's in the solution if you want to look at it or work it out. But basically you just don't get any stagnation points. And that's why the question says, if any. So it should be a common. Okay. Does anybody want to do part D? Yeah. Huh? You want to see part? Okay, you want to see part D. Okay. Give me a second. I gotta add a page. I gotta figure out how to add a page. Let's see. It's funny because on my computer, the letters are not showing up. So, oh, there they go. Okay. Okay. Now we have another page. So we're now on part D. So the problem in part D, determine the dynamic pressure differences or difference between two separate concentric circles in the flow field. The first with R equals 1, the second with R equals 2, both centered at the origin. So what we want to find is, come on. Here we go. P1 minus P2 equals delta P. Where P1 equals the static pressure at R equals 1, P2 equals static pressure at R equals 2. Okay. Specifically, it asks about the dynamic pressure difference, right? So when I'm writing P here, I'm not necessarily talking about the static pressure. I'm just saying what I could, what's a good way to put this? Here's a good way to put this. I'll get rid of the P's just to make it, I think, less confusing. We'll make it Q. Q is typically the variable that we'll use for dynamic pressure, and that's in this class, 306, 312, like a lot of across aerodynamics, you'll see Q kind of used as the variable for dynamic pressure. So we're trying to find delta Q. So what's the first relation we're going to need? What is the definition of dynamic pressure?
Isn't just 1/2 whatever being used for?
Yeah. So we define a dynamic pressure as, write it up here, Q equals 1/2 rho V infinity squared, or U infinity squared, right? It's same thing. And honestly, if it's free stream dynamic pressure, then it's 1/2 rho V squared, V infinity squared. But we're talking about the dynamic pressure at kind of a specific spot. It's at any point along the arc of the cylinder there, but we're talking about specific locations. So I'm going to obviously drop the subscript for V infinity. So we have the change in the dynamic pressure between these two positions. So we have 1/2 rho V1 squared minus 1/2 rho V2 squared. Now what? What was that?
Find V1 and V2.
Find 1 and V2. So how do we find V1 and V2? Yeah. Take the derivatives of the stream function. So for the radial component, well, actually, I'll back up even from there. I'll just write this for you guys to hurry this along. Right? In the same way that that's true in cylindrical coordinates, right? It's still the same idea where we have a vector, two vectors, and to find the magnitude of them, you just take the square root of the squares of both. We're working with the square of the velocity, so just eliminate the square root, not even bother. But so we can find, yeah, the velocity components from the stream function that we have back up here. So if we do that, what we get is u theta equals, what's the equation for u theta for the string function? Cylindrical coordinates. Here you go. And that's going to equal positive u(a) squared over r squared times sine theta. Right, because we bring the r up, we bring the negative down, we subtract it, so it goes back in the denominator of the square. The negative cancels out with the negative out in front, so now it's positive. UR, what's the relation for that?
Whatever our part to the side.
Okay. In this case, we keep the negative. We have u(a) squared, still have the r squared because of 1 over r. And then this, the sign becomes cosine. Okay. So now to find the velocity magnitude, what we get is v1. Well, I'll drop the subscript here just to keep it more applicable. What we have is u over a squared, or u times a squared, excuse me, over r squared, sine theta squared, plus, sorry, just trying to get the zoom thing out of the way. Here we go. Plus negative u(a) squared over r squared cosine theta. And so if you're looking at this, you're kind of seeing the writing on the wall, right? Where you're like, okay, sine squared plus cosine squared equals 1. So that aspect of it's going to go away. We can combine the terms, or when we do that, we are factoring out the rest of it. And so what we end up getting is u squared a to the 4th over r to the 4th. And now all we have to do, v1 squared equals u squared a to the 4th over 1 to the 4th oops. V2 squared equals u squared a to the fourth over 2 to the fourth. And now what? You just look so energized that when I ask you. Yeah. 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 There you go. And then we're done, right? And we can all go home. U squared a to the fourth over basically 1 minus 1 over 16. Oops, don't need that. There is one caveat, right? What we actually had to find was the change in Q. So there's a 1/2 out in front, right? So our, and the density, yeah. So what we're going to get for this is this is 15/16 over here, right? So we end up getting 15/30 seconds rho u squared a to the fourth. That's the answer.
Given stuff like density of the example.
It depends on the problem.
If you want to do it.
Yeah, I mean, I know sometimes it feels more comfortable to plug in numbers and see if, I don't know, see things reduce or something. It is easier to sometimes gut check if a number makes sense or not, right? If you're looking at a giant relation as opposed to you plug in numbers and you're like, oh, I think this velocity should be 50 feet-ish, 50 feet per second-ish, and you come out and you plug in numbers and you're like, wow, I got 2,000 feet per second. That feels pretty wrong. There'll be some problems that are and some problems that aren't. That's all I can say. But there's some problems that are. So.
Question, would you elaborate on the differences between like static pressure, dynamic pressure, pressure, all that? Because they kind of get mixed up in the mechanics. I'm not really sure what it.
Yeah. So atmospheric pressure is just the static pressure in the atmosphere where you are, right? And here, static pressure is, probably a little over 1 bar or about 1 bar, 100,000 kilopascals, give or take, right? If you are considering a moving flow, now you're adding a dynamic component to that, right? But if you're considering the free stream, it's still going to just have that ambient static pressure. You're just adding that dynamic component to it. And that's summing up to be a stagnation pressure or total pressure. So if you're at a condition, right, if you're considering a wind tunnel, right, and the static pressure in there might not be atmospheric, but just for the sake of the argument, say that it is. As you speed up the tunnel and you say if you assume that atmospheric pressure stays the same, you're increasing the stagnation pressure, which is the pressure you'd have if you brought the flow to rest, right, against something, right? If you brought it to stagnation, right, all the energy was taken into just, component of basically static pressure from bringing the flow to rest. Okay.
Yeah, but like we're like okay, so for like the first slope of the problem where the last slope was like a height, and you had to you got the pressure at you got to find the pressure.
Yeah.
Like what's the intuition behind the static pressure? The static pressure I kind of see it's like pressure with the dynamic pressure. Is it like dynamic pressure acting like
The static pressure is the only thing that's exerting a force on anything. The dynamic pressure is by the fluid moving, it kind of takes away the ability it has to exert force on things.
So it's like static pressure that reduced by having movement of the fluid.
Yeah. Right, it's kind of, I wouldn't say it's creating a vacuum, but having the flow moving over something, way to describe this.
The stagnation pressure is basically like the first two terms of the Bernoulli equation.
Yeah, and the gravitational term could show up there too. But we don't typically consider it.
Have high
Air,
frequency.
yeah.
So your
But
stagnation.
yes, the stagnation pressure exactly is if you brought flow to rest.
And your half rho v square, second term, is your dynamic pressure.
1/2 rho v squared is dynamic pressure.
And the p term which we use there is the static.
It's just a static pressure.
Okay.
And the Navier-Stokes equation, to kind of get back to your question, the Navier-Stokes equations have static pressure.
Also,
Yeah.
coefficient of pressure, the little Q infinity, is that dynamic pressure?
Yes. That's free stream dynamic pressure. Yeah.
Little Q is dynamic.
Little q is dynamic pressure. The subscript or whatever will kind of tell you if it's local. Because again, it's going to change all around, say, the cylinder, right? The velocity is changing all the way around it. The density is staying the same. So the dynamic pressure is changing all the way around the cylinder. The total pressure is staying the same. And what you're basically trading off is the static pressure and dynamic pressure, right? As one goes up, the other goes down.
Is that in like the homework where inside the pipe the pressure is constant? Is that because the flow's incompressible?
That was because we made a crap ton of bunch of assumptions. All the assumptions that we need for Bernoulli's, that's what we made for that.
Okay.
So that we're assuming, for that case, we assumed it's irrotational. We didn't necessarily have to, but yeah, we assumed it's inviscid, it's incompressible, it's irrotational, steady. Yeah.
Okay.
Ladies again, like so you will just trade off between static and dynamic. And why we're not just using static, but we're using
Yeah. I mean, basically, as the flow accelerates, right, or as it goes faster, I guess the way to think about it in a sense is it has less time to exert a force or pressure on something, right? And so, yeah, as you go around the cylinder, right, top of the cylinder, the velocity is 2v infinity, right? The front, if it's not spinning or anything, right, you have stagnation, and the velocity is 0. And so whatever you have for the dynamic component is now added to the static component, and that's what's pushing against the cylinder. As you go up and you get to the top and the flow is accelerated to its maximum rate, you have the least static pressure. And so it's, yeah, there's not as much force acting. What this typically turns into for something like an airplane, right, is the flow on the lower surface has roughly atmospheric pressure, maybe a little higher, maybe a little lower. And the upper surface typically has a lot lower pressure. And so you get like a suction up. But that's because we're talking about like the net when you go all the way around the airfoil. But yeah, on the cylinder, right, since it's symmetric, you get, as it speeds up to the top and at the maximum velocity, you have the lowest static pressure. And then as you come back down, and again, we're talking about potential flow, so we have this full recovery. We're getting all the way back to the other stagnation point. And we've now recovered to where the velocity is 0 again. We have full stagnation pressure. And then as you go off, the flow actually accelerates again. We don't typically work with that because we don't really care, but. Yeah.
So your stagnation pressure is sort of like conserved, like it sort of moves between static pressure and dynamic pressure. And it's fully in static pressure when your V is 0. And it is mostly in dynamic pressure where your V is the maximum.
It depends on the case you're looking at, but yeah, it's basically, it's always the sum of both.
And it's constant.
It's constant. When we satisfy all Bernoulli's equations assumptions,
Then it's a
which is the only times that Bernoulli's relation is valid.
Yeah.
But that's kind of the whole idea, is that yes, you're going to have this total, it has a lot of names: total pressure, total head, stagnation pressure. I think it's just go ask the people in the 40s why I don't know. But total head's another one that you'll see. Not so much in our field. I feel like that's more in like HVAC systems and stuff that we'll talk about this. But yes, the stagnation pressure, constant, and basically the other pressures are just trading each other off as you figure things out. Or again, one increases, the other is going to decrease proportionally. Everybody feel thoroughly exhausted? What's up?
For the solution on problem 2, you take more of the K component. Is there a reason for that?
Column 2. Ignore the K component.
Oh.
In a solution? Not necessarily. I was doing this also on separate paper and I worked it out and just confirmed that everything was closing nicely. You'll put it this way. You could use the K component and solve for the coefficients and you'll get the same coefficients. If you want to prove that, you're going to tell me you can't.
Coefficients, but they don't cancel out to 0 in the K.
Let me see. So we have partial y, partial x. I have room over here, so I'll do it over here. For the K component, we have partial uy, partial x, minus partial ux, partial y. What I had found in the solution is b equals negative 5/4, a equals 5/2. So for this component, what we get is x 5/4. We get 5 yz squared, right? Because we have the negative that cancels the negative. And then the only thing that goes away is the x. And we have a negative. There's partial x, partial y. So you end up getting 6 times a, which gives us 15. 6 times 5 halves. Y z squared minus, and we do take partial y, so it's going to be minus 10 y z squared. We want that to equal 0, or it should equal 0. Which does, right? Because we get negative 15 y z squared plus 10 y z squared. I promise I can do math sometimes, just not all the time.
So you don't have to on something math and things.
Yeah.
No, you're expected to be perfect. I'm sorry.
No.
I can strongly encourage you to just caffeinate as much as you can.
No.
I'm not a health expert.
If we just take it over, do it over the break and we get that.
I think so. I'll put it this way. How does everybody feel with like the first problem we did? Right, we have the two vortices. Beyond the confusion on counter rotating and all that stuff, right? Beyond the not syntax. I don't know why I'm blanking on the word. It's I gotta go home and write an abstract too. Beyond the convention of what's positive and negative, you feel generally comfortable with the whole process? Same with the spinning cylinder, right? Familiar with the whole process? Yeah. Right, you take the stream function or velocity potential, one or the other. You add up all the elements that you're concerned with, right? And then take the derivative to get the velocity components. And then from there, it's doing some calculus and doing some trig, right? Typically. You might have to use Bernoulli's to get the pressure somewhere, or again, whatever. You could, the one homework problem has where you have to integrate along a surface. That's very possible, although kind of lengthy. So I don't know if that'd make a decent exam problem. But yeah, there's a lot of avenues to go from there. But then that's kind of the creative engineering thing of depending on what the problem requires of you, right? The thing I would say is just be really careful about signs, even beyond this, the cylinder stuff, right? You just remember that the streamline, for example, the stream function, if you're taking a derivative, there's usually a negative in front. Not always, but depending on the thing, there's a negative in front. It's easy to lose negatives even in the problem. It's just kind of, you got to keep things consistent, or keep them tight just to make sure you don't lose those kind of bits. But yeah, other than that, it's pretty straightforward calculus and stuff, right? Sometimes you have to do a substitution or whatever, but you know, it's pretty straightforward. The one homework problem, again, the one that's not going to be graded very rigorously or anything, but the concept there where you have to use Bernoulli's with conservation of momentum, I would at least be, again, familiar with that kind of general process, right? Or you, and maybe again, same idea of conservation of mass, because that's another one. Basically, the control volume kind of stuff, partnered with Bernoulli's relation or equation, to then solve for problems, because it gives you this ability to take pressures and then get velocities or vice versa, right? So you can have a lot more information available to you by solving things. And then other than that, I would want to know, again, like, I mean, some stuff we're doing here. Does everybody feel comfortable with this problem, for example? Yeah. You moved. I was looking over there for you, but you moved. Yeah, you snuck around. I don't know. Do you feel fine with this idea? This is pretty just straightforward calculus. Again, if you don't know how to do it, go check in the notes, or you know, it's taking the curl, right? Ultimately, you would need to do is this. So, you know, I'd know how to do that, what that looks like, have that available. But you know, there's only so many things that we can do with these things. Yeah, I guess the circulation one, like I said, any problem that involves it is going to tell you the correct convention to use, or requires the magnitude where the convention doesn't matter. So that's okay. And then other than that, yeah, I'd also try to, again, go make sure you know the concepts, kind of the basics things. Again, like when we're deriving the string function, what's kind of the fundamental assumption we're making in there?
Conservation.
Yeah, well, it's conservation of mass. We're using conservation of mass. There's something specific we're doing with it. Yeah. Yeah, we're assuming the flow is incompressible. So that's what we're kind of fundamentally building on. What's the one for the velocity potential that we're kind of, again, we're defining the velocity potential as being valid because this is true.
Irrotationality.
Yeah, right. It's the cross, del cross velocity vector equals 0 is fundamentally where we're getting it from, right? We're deriving it from. So things like that, keeping those in mind. View the streamlines, path lines. You haven't.
Really go over the thing or just think on it? It is, or you say?
That's the spirit. All right, so streamline. What's the definition of a streamline? It's tangent to the velocity at all points. I mean, that's in a formal sense, that's about, you know, all to know. I mean, the streamlines themselves, you can solve for individual ones, right? So it's but it's not necessarily following any specific particle, fluid, or anything like that, right? It's just the tangent to the velocity vector. So depending where they start, they're always going to stay tangent to the velocity vector as they progress in space, or as you follow that point in space, or go just staying tangent to the velocity vector. What about a path line? Yeah. Yeah, so the path line is just the trace that a single particle makes in time, right? So you drop it and it does this. That's the path line. So even if the flow is unsteady, basically once that particle has passed a point, that point doesn't move anymore, right? It's just wherever that particle went, even if it's an unsteady flow, right? The path line is basically, as the particle moves, the path is defined, the path just is the path, okay? And then the last one is a streak line. Anybody want to take a crack at the streak line?
It's like all the instantaneous particles at a given moment.
Yes, the streak line, if it's an unsteady flow, does change with time, right? Imagine you have dye and you're letting it into a flow that's doing this, right? There's dye entering, and the flow field itself is kind of a sine wave that's going back and forth. The dye is going to do this, and over time, it's going to be doing this as well, right? You check an instant in time, and it's going to be totally different, right? You check another instant in time, it's all going to be totally different. The path line, if you release it at a different time, you would get a different path. But if I release it at time 0 and I just keep following one particle, where it has gone is not going to change, right? Just if I released it at a different time, I would get a different where it went. Where the streak line is actively changing in time, because once the dye is released, you're kind of following a whole line of things, and they're all kind of moving in time.
Are we gonna have to know the equations behind?
You're going to have to draw that as a function of time. Sorry, what? Are you going to have the equations or something?
I was asking if we had if we had to know the equations for this, or if this was more so like we just have to know these specific concepts about.
So like for the path line, for example, we did have, I think, a homework problem or two where it's like, hey, here's a particle in space. Like a lot of those ones where it's like, here's some random polynomial and it's also a function of time are basically path lines. You're following a particle through time and wherever it goes and whatever it does. So in theory, yeah, there could be like, hey, here's the path line for, a particle. And again, the path line be given as like r, right? It's a vector in space. And so if it's find the derivative or find the velocity, I just get either way. If it's find the velocity, then you have to take the derivative, right? And say if the position is just x, if you take the time derivative of x, it's 0, so it's not moving. But yeah, it'd be given to you like, here's the position of this particle as it moves. So that we could do. The streak line, probably do in a similar way, but yeah, we have not done any where we've like mathematically defined a streak line and then done stuff with it.
For a streak line, would it essentially be just an equation?
Both the path line and the streak line do not have to be a function of t, right? If they're not functions of t, if the flow is steady, right, all three of them are the same. They end up overlaying on each other. It's only when the flow is unsteady that you get the path line and the streak line are not going to be the same.
For the streak line, how would you draw it? Like, path line's fine, you just draw a path of the particle.
Nobody's asking you to draw a streak line. That would just be that would be cruel and unusual punishment. And I'm only into the cruel punishment.
Redefine the streak line again.
Yeah, it's
the locus of all the points that pass through a point. Like
yes.
all the particles that pass through a point.
What he said. So if we have. Oh, okay. Is this like being recorded for TikTok or something? We have dye is being injected. Is this still, okay, it is still showing. Right, and we have U, and U is a function of T. So this locus of points that have passed through a single point, right? The entrance here being the single point. At T later, it might look something like this. Right? Because the particle, the specific particle that was here is now over here. And the particle that was here is now here. Actually, I shouldn't draw that one. I should say the particle that was here is now here. And the particle that was here is now here. And the particle that was here is, I don't know, here or something, right? You'd have to have the actual flows, like velocity field to say how far they moved and stuff. But basically you get where it's this coherent series of points, right? Basically curve or whatever, right? That's, say if you did like pulsed bubbles every quarter second or something, which is basically what happened in the video, you're going to get a coherent path or streak line, again, of these particles moving. Like I said, the path line, on the other hand, is I release it from here. And at dt later, it's here. So we'll call that dt1. At dt2, it's up here. At dt3, it's over here. Really, it should be T1, T2, T3.
So that's.
But the rest of the path line's not moving, right? Once I get to T3, T2 and T1 are still the same spot. That's where that particle that I'm following went through.
That's where it was at those different times.
Yes,
So
that's
it's
where it
not-
was at those different times.
So we're taking kind of a snapshot of multiple different times.
Yeah.
For that, but for the actual streak line, we're kind of just saying at one time, this is where all of the particles are.
Yes.
And
Yeah.
then at a different time, there's some different streak line because the particles are changed. If it's an unsteady flow, there's
Yeah.
steady flow, should just stay the same.
Steady flow, they're all the same.
And if you go back to question 3 and then instead of a full cylinder, you have a half cylinder, does that like change anything?
Ooh, that's a good question.
I mean, is it still a doublet or?
Does it change anything? What does it change?
Data.
Change what? Theta. Why does it change theta?
Like 0 to pi? I think he's saying.
Oh. Yeah, so like in the homework problem, yes, it changes where you're integrating from 0 to pi instead of 0 to 2 pi as you go around. That's true. In terms of depending on what you're looking for, right? What do we do for the method of images?
Identical. In this case, it'd be a doublet, like. The radius would be mirrored across the axis that it was sitting on. And so.
Yeah. Yeah. So a doublet on the origin is effectively, if it's not spinning, right, is a reflection of itself. And so it's just, if you had a doublet where, again, like the Quinsett hut in the homework problem, where you have a doublet and a free stream, you just do everything the same as a doublet. You just don't evaluate the velocity down here because that's underground.
But what if it is?
What if it is spinning? And it's a half cylinder? Don't worry about it. Yeah, I mean, like this, like if you have what, like Heelys, we have a Heely that we're spinning the wheel or something, like. I'd have to think about that. But yeah, the answer is don't worry about it. Yeah. But if you do have a half cylinder that's not spinning, you treat it as if it's just a regular
So
doublet.
you just change your integration terms.
If you're looking for integrating forces and stuff, yeah.
Yeah.
And then it's not nothing like that spends it like half, right? So it's still the same. It's not like,
Strength's still the same.
it's not half, it is half.
Yep. Strength is still the same.
What happens if your half cylinder is not at the origin, it's above?
Like, can we just change the origin
Yeah. Huh?
It's not.
Calculate the R for a half cylinder?
The R distance from the, like,
It's
original,
not.
since above the axis, you saying calculate the R from the.
Yeah, I mean,
cylinders.
the only reason you wouldn't have it on the origin if you're trying to do that is like, say you have the ground and you have a half cylinder. Don't worry about it. I don't know why you guys, like, again, cruel and unusual punishment, and just a cruel punishment. This is unusual. Trust me, the cruel punishment is tough enough. You don't have to worry about the unusual.
Yeah, it's so bad.
I don't know if that one was that hard as much as it was long.
What was question 3?
What was question 3? The one with the barge?
You didn't look at it, I just saw it in the map.
Yeah.
Pretty straightforward.
I said I was so fast.
Well, I'll put it this way. I had the TAs look at it, and all 3 think it's fair. They think it's concise. They think it's straightforward. They think things are explained well. You could say they're just a bunch of sycophants, and so, you know, they're just telling me what I want to think. So I'm looking forward to hearing what you guys think tomorrow. I think it's pretty doable in the amount of time. If you feel comfortable with things we've talked about today, especially, you know, the things we've worked out and stuff, should do fine. Again, the process for especially potential flow problems, it's generally you start in the same spot. You define the flow field with either the velocity potential or the stream function, get the derivative, take the derivatives to get velocities, rank through whatever you need to do from there, right? Again, keep in mind, you can find the velocity not just on the surface of the cylinder. You can find the velocity anywhere out in space, as we did with the vortex problem, right? That was kind of the idea there. We found the velocity just at these arbitrary points in space. So. I think they're fun problems. I think they're actually like pretty good, like applied aero type problems. So I'm kind of excited.
Like,
So hard. Like.
I don't know.
It's gonna be like.
All right. Any other final thoughts? I'm starting to lose my voice.
No,
So.
I would say.
Uh-oh.
Stagnation 0 at like.
Stagnation?
Yeah, what, so you said that, like, what would it be, just be zero, because you really checked earlier, you said I had to like correct when the sine and cosine is like equal to these points.
Yeah, there was a caveat. I think I screwed that up
Like right
during
here.
office hours.
Yeah.
Because we end up getting a sine, sine equals theta, or sine theta equals cosine theta equals 0.
These two have
And
to-
that's where they both have to be 0 at the same
Oh,
time, and
but
there's
it's not-
not a
It's
place.
not possible though, because in the unit circle, they're never equal to each other.
Yeah, so there's no stagnation points.
Oh, okay.
Yeah.
And I have a quick question, another quick question. So, did you get the E data from, earlier for one of the
About doing
problems?
the circulation,
Yeah, where'd you get the E data?
that's the tangent to the
Oh,
Uh,
okay.
thing in which, yeah.
Oh, okay. So if it's normal, then
We're
EPR
basically drawing the circumference of our cylinder as our path of integration. And so, yeah,
Okay.
E theta is just around it.
And one more question. From the one you did earlier from office hours, if we had like a vortex spinning, would these two be 2 doublets and 2 vortex and a uniform flow?
Yeah.
Okay. And then you just basically take the derivative and solve for each one. And then because it's not near the origin, we have to take account from the R. And that's
You
really-
might eventually end up with something really goofy depending on how big gamma is,
Oh, okay.
because you're gonna get where like the stagnation point starts moving off the cylinder, right? It's spinning fast enough,
Yeah.
and it might start moving into the other cylinder.
Oh, okay.
And so things are gonna get
But
weird.
this is like the hardest one you can give us, right? Somewhat.
Because like I understand. that-
Somewhat.
Like,
Sure, what? Like, I feel like these are just pretty consistent. Just say, take the streamline function, take a derivative, and find whatever you need. Is that mostly what the idea
It's
is?
a randomly
Right?
problem.
Which is why it's so cool.
It's not cool.
It is cool.
For the first one.
So, botch. No, I'm not sure we did. I'm just not sure how we got.
That's not a bad, it's not a bad.
Next one is the,
We have
the last.
basically,
This was, no, this was, showing this.
we take this square root of this, or we get ln of.
Yeah, we moved the 1/2 outside. So that's like an exponent.
Okay.
And you've got the natural log of something.
Yeah.
And it's to an exponent, you can move that exponent out front as a coefficient.
Yeah.
Okay, and that's why there's a 1/2 outside down after it's 4.
Well, the 1/2 is coming from the definition of the,
Oh,
is that coming vortex.
from?
that's coming from the vortex is gamma over 2 pi,
Okay,
ln of r.
but then there's another 2 that comes out.
And that is from the square root.
So we have ln of square root of x minus b over 2 squared.
Yep.
And that simplifies, so basically if you have like ln of square root of something,
Yes.
oh, that's the same as ln times something to the 1/2, and
Yeah.
you bring the 1/2 down.
Yeah.
And that's why it becomes 4 pi.
Yeah.
Okay, that's all I was confused about.
Yep.
And then from after that, we basically just evaluate at the point.
Yeah, like, you
Yep.
can say that in the problem.
Like what?
Okay, I think I understand the
Like,
process pretty well. It's just like getting through the math to
Whatever is
get to
zero,
that.
then you use.
Without fumbling the ball somewhere.
Yeah.
Tricky.
Yeah.
But
Okay.
it's not
Well,
possible.
thank you, yeah.
Yeah, but
Yeah,
then put that in the problem to like make sure we know how, right? And then, yeah, but then they would
How come
find
that
it with
would
either
come off?
Pathfinder or tree function or the other.
Yeah, I mean, this.
Actually,
kind of.
I figured out how to do this. It's the
Okay.
kind as approved.
Okay. What's that?
Here.
Wait, I have a question. Can you give us more example problems? Cause I feel like I don't have enough.
It's too late now.
No, like, I wanna go over the night,
Cooked at this point.
24 hours before like. Can you make up one that's top of your head?
Only if you stop leaving gum on the
I'm
podium.
not. What you would
Yeah,
do?
No, maybe it was true. I looked up in the last time.
You were chewing gum too, like like something hard, but like similar difficulty on the exam. Let's say that.
You like football?
Eh. I like airplanes. Of course. Why? Yeah. Of course, you're gonna give us an airfoil, right?
Oh, it is a ring.
That's a creepy smile. Look at that. That's a creepy smile.
A Rankine oval, this is kind of rounded off, but whatever. You can pretend it's football.
Okay. It looks creepy though.
So you've got a Rankine oval.
Oh my god, it's a uniform flow now. Why would you? You have to take it
And
at an
it'll
angle?
tag.
Yeah, fine.
How would you do
Figure
that?
out.
Say this on you.
Oh no, how would you do that?
I don't know if this would work, but you can try it.
Oh,
The
and then this is
circulation
vortex right there,
that
and
puts
then
the
double
stagnation
it.
point
Would it be a
on
double
the
too?
x-axis.
So would that create another double?
That creates another double.
No, it's just a source and a sink.
The source,
Oh,
it's the
so
same with the vortex. And then you want to find that
How
puts
do
the
we know that
stagnation point
those two
on the
points
back.
are source and sink.
Because it's a Rankine oval. you said.
Yeah.
Those sourcing.
Like, how do we know? Like,
We just
if we look at
redirected
it.
it.
Yeah, we derived it. It's how we got to a double, right? We moved these like.
Oh, because like a double isn't like a source and a sink like close to each other. Is that okay? So you can assume that's a double basically.
No, but it's not a double.
They're not
They're a
close enough.
finite difference apart.
Oh, unless they're like super close.
They're on top of each other. Yeah, it's-
Okay,
it's
so then
enough.
they
We know
don't
the
have a
distance
radius
between-
basically, like in the X direction.
It's, this is not the same model as the double, it's a different model, it's just, here we're modeling as a source.
I better not see this on the exam.
Why not?
It's horrible.
How would you
It's
deal with,
unusable.
how would you deal with?
Yeah, how would you deal with this one? Would you take the cosine and sine components?
Break it up.
Figure it out.
You have 2 years.
How did we, let me end the Zoom real quick.
This is a good one. Yeah, you should have just pulled up exam to right now.
It's totally
So right now. Just like the accident just went over the exam so. Wait, is that the lingo? Oh my God.
That's my,
That's your daily like class of clang, I guess.
you can look, it hasn't been used in like 3 weeks. I'm pretty sure that's my daughter is using that. We were starting to try to learn German. How the hell do I get Zoom back? Here we go.
It's just speaking German to you.